Welcome to day 7 of the advent of compiler optimization. Today we're going to look at division by things that aren't powers of 2. And to make it a bit more interesting, I'm going to use an integer to ASCII routine as a way of showing the kinds of things that compilers do for us for these kinds of cases. So let's have a look at one. Writing an integer to ASCII converter is kind of interesting. The way that I do it is to take the value and keep dividing it by 10 and using the remainder as the digit as you go. And you keep dividing by 10 until you get 0, which means that you've reached the end of the value. There's no more digits. And each time you've modded, you've got one more of the digits of the output number, which you then add to the ASCII value for 0, and there's your number. Now, doing it that way gives you the values backwards, and I'm going to ignore that for now. There are many tricks for generating them in the correct order or for working out how to write them backwards. We're not going to get into those now, although it is a really fascinating area. So let's start. So I'm going to do void int to ASCII backwards, and we're going to take an integer x, and we're going to take a char star buff, and we're not going to check the value or the distance or the size of that value, that buffer, sorry. So I'm going to do, and this is while x. This is the one and only place that I find do while useful, is writing this particular routine. So I'm going to say star buff plus plus, I'm going to write to buffer, is equal to x mod 10, which gives us the digit. And I'm going to do plus the ASCII value for 0. And then I'm going to do x divided equals by 10. And I'm going to assume the value is positive. In fact, let's make it explicitly so. Let's do unsigned here, and then we'll just make this uint to ASCII backwards. And here the compiler is telling me, what is it telling me? Oh yes, I'm converting from signed to unsigned here, so let me put a U on there and a U on there. And we're still getting this because I'm going to have to static cast this to be unsigned as well. Am I? No. No. Okay, hang on. What is going on here? This needs to be static cast of char. There we go. Got there in the end. Just goes to show that I'm not that great at writing C++. So what have we got? We've got a function on the right-hand side that is dividing by 10 and modding by 10 each time. And modding by 10 is getting the remainder of a division by 10. So modulus also requires a divide. The first thing that's happened is the compiler has spotted that having divided by 10 and got the remainder, it doesn't have to do it again. So there is only one operation that's going on the right-hand side, which we're going to dig into in a second. There aren't like two divide and moduluses that are separate. But if you're looking already on the right-hand side, you probably noticed something. There is no divide instruction on the right-hand side at all. We've got some zany-looking constant in R8. We have a loop between L2 here of all these bits of code, all these opcodes. And then we have an imul in the middle, which is an integer multiply. What on earth is going on here? Let's trace it through and see. The first thing is that we can see that this constant is CCCCCCCD, which is kind of a weird repeating looking number. So maybe we can get a clue from that. We're moving some things around. We're taking a copy of the original number. We're adding 1 to RSI. I'm going to assume that RSI here, it's the second parameter. This is our buff. So this is where we're going to be writing the output to. So we've kind of already added 1 to that. We've got copies of the input in EAX and EDX. We're then multiplying RAX, which is the EAX register, but all 64 bits of it, with R8, this strange constant up here, this 3, 4, and so on, and whatever. CCCCCD. So we've multiplied our value by some huge number, and then we're shifting right RAX by 35. So our integer value that came in, which was 32-bit, was multiplied by another 32-bit number. When you multiply two 32-bit numbers together, you get a 64-bit answer, which is what our RAX now contains. And then we're shifting that right by 35. Interesting. Okay. Then we're doing an LEA, and we're doing racks plus racks times 4. Now, you've seen the earlier videos we've done on multiplication. You know that this is a multiply by 5, and then it's adding ECX to itself. So we're multiplying by 10 here. So why are we multiplying by 10? Finally, we're subtracting from the value that we have in ECX, adding 48 to it, and then doing some looping stuff. So what's happened here? Well, I'm going to now switch over. I'm going to copy this value, this magical value up here, and I'm going to switch over to Python. And what we're going to do is we're going to say def result x, and then we're going to say return x times that magic number. And then, oh gosh, I can't type. Shifted down 35. And then I'm actually going to execute this code on the right hand side. Execute the code. And then we're going to look at the output. And the output is going to go here. Program returns 0. So what if I did print result of 10? What do we get? 1. What about 12? 1. What about 1, 2, 3, 1, 2, 3? 1, 2, 3. So this sequence of operations is appearing to divide by 10. This value here, 3, 4, whatever, if we now divide that through, let's just print the results of that divided by 2 to the power of 35, we can see that that value is 0.10000582077. So the compiler has realized that you can synthesize a divide by 10 by multiplying by 1/10. But we're using integers. How can it be multiplying and getting an integer result like this? Well, by doing the multiply first and then shifting down, we're effectively using fixed point precision. And the compiler is able to show that for all of the values, all of the range of an unsigned value, this will give the right answer. So our division is done by a multiply and a shift. How cool is that? This is only true because we're dividing by a constant. The compiler has a number of tricks and it can build a division by a constant out of many different approaches. This is one of them. So even if the range of the input and outputs don't allow for this exact trick, there's usually 1 or 2 patch-up instructions that the compiler will add to deal with rounding if the rounding doesn't exactly work. But for division by 10, this works perfectly. So we've done a division by 10, then we do a multiplication by 10. And then we subtract the numbers that we first had. So by taking our number, say 123, dividing it by 10 to get 12, and then multiplying it by 10 to get 120, we then use the difference between our first number, 123, and 120 to get that last digit, the 3. So 123 minus 120 is 3. That's our modulus, that's our last digit. And that's what's happening here. We're just subtracting the 2 and then adding 48. 48 is the ASCII value for a 0, as it shows here. And then we're checking to see whether or not there's any need to loop round again. By the compiler has done some clever loop tricks here. We'll talk about loop tricks later on. Then we write our value in, and because we've already done the increment, we have to write it in at address -1. Again, that's another kind of clever trick the compiler does to move work earlier in the loop. So our ASCII routine contains no divisions at all, despite on its face having 2. Just quickly to demonstrate, let's do some other divisions so you can see the other types of instructions that the compiler generates. So here it has done something quite, I'm using ints again. Let's use unsigned here. So the fact that it's generated slightly different code means that it's accounting for the negative rounding modes again. But if we just make it unsigned and make this unsigned and do over 10u, you can see that same constant we saw in our ASCII case here of dividing by 10. And then let's try some other values. If I did 1, 2, 3, you'll see that the code usually generates a little bit more. So in this particular instance here, it had to account for something different in the way that 123 shakes out. There's a whole algorithm for determining the instructions for this. But just know that if you know that you have a constant, then the compiler will generate the right sequences of instructions for you. Let's say try some other ones just quickly. And you can see, yeah, there's a number of different patterns of instructions it'll generate. Hopefully that makes some kind of sense. The compiler has your back as always. It knows all the tricks to generate all the different types of sequences of instructions that can generate a division by a constant if it knows that constant at compile time. Tomorrow we'll be looking at some loops. I hope to see you then.